Okay.
Okay, yeah, let's start it. Good afternoon, everyone. Welcome to the HAO colloquium. Today I'm taking Nick's duty to chair this colloquium, and which I'm very happy to do because the speaker is my older friend. Let me see. Okay, got a one in. Yeah. So the speaker today is Dr. Banashi Ferdowsi. We used to call her Bashi. Um, Bashi is currently serving as an assistant research professor in the Institute for the Study of Earth, Oceans, and Space, or EOS, at the University of New Hampshire. Her current research focuses on the understanding of magnetosphere, ionosphere, thermosphere coupling using first principles-based modeling approaches and data-driven methods. Bashi holds a bachelor's degree in physics from the Azad University in Iran and has also received a master's degree in high energy physics from the Southern Methodist University, SMU, in Texas. She obtained her PhD degree in the Department of Space Plasma Physics from the University of New Hampshire in 2017. She was advised by Professor Jimmy Reeder, and her thesis was on the study of magnetohydrodynamics and their atmospheric signatures using the global model OpenGGCM. Bashi is an expert on numerical modeling approaches and machine learning. Along with her current position at UNH, she is also a domain researcher for the NASA Frontier Development Lab, or FDL, working on understanding the geo-effectiveness of solar storms. And today, Bashi will talk about global geomagnetic perturbation forecasting using deep learning. So take it away, Bashi.
Thank you so much for the nice introduction, and good to see you, everyone. I'm going to turn off my camera and then share my screen. And okay. Right. So thank you so much, everyone, for coming. And today I'm going to talk about our latest model in forecasting magnetic field perturbation on the Earth using deep learning. This model was developed by me and our team during the FDL 2020. A little bit background of so these are my great visual panels, and two are the researchers, and many were the researchers who mainly developed the models, and then Mark, Osti, and Ryan, Sida, and Yarin were our mentors for that challenge. So let me give you a little bit background of what is FDL and what we are doing here. So Frontier Development Lab is just kind of place that is gathers people from research and people from machine learning and AI domain, and works on a national hazard problems. So the problems that they usually tackle are could be for flooding, for example thunderstorms, for lightning, for human in space, or going to the moon. So basically what happens is that in places like Google or NVIDIA, these places, they give us the tools, and then other places like NASA provides the research, the topics. And basically they have the teams are consistent of half of from research domain and half from machine learning domain. And what they do, they come in a room and then they try to tackle one problem together. In this challenge, the effectiveness was one of the challenges that we started, and then ended up this nice machine learning model to forecast DBDT. So why do we care about forecasting DBDT? So basically, I think in this group presentation is easy. Everyone is probably familiar with geomagnetically induced currents, and they can impose critical hazards for our technology, especially our transformers. And they can interrupt our telecommunication systems. They could interrupt the railways and pipelines, and they could lead to widespread blackout, and it has been in the history, like in the Quebec in 80s, and then there was these it was Carrington event, that you all know, long time ago, that was these geomagnetic storms that interrupted the only technology which was back then, the telegraphs, and then set fires on them. And so yeah, so it's important for us to study these GICs, and an estimation of them are reliable estimation of them are really needed for mitigation on the Earth. And as you probably know, that GIC data is not conveniently accessible. Like recently, some power companies started like sharing it with us, but it's like, for only for like special, like, extreme storms, but they're not very for no, like, for all the data. So another things that we have, which is I call it the sister of GIC, is ground magnetic field perturbations. And it's a good proxy for predicting GIC right now. And as you can see on the right side, you can see, so let me see if I can get my laser pointer. Okay, as you can see here, these are the station of Supermax. So we have some measurement all over the world for Supermax. So our aim for this model was to create a high resolution, both in spatial and temporal, global model of dB and dB/dt with predictive lead time using machine learning techniques. So I want to go a little bit on the previous studies and say why do we need to have another model. So this is probably, and you have seen it, this is a study by Pulkin in 2013. And basically in 2013, Antti Pulkkinen from NASA, he compared couple of like heavy used models in the community. There was including some empirical models that I first focused on, Weigel and Weimer, and then there was a couple of three numerical model, which is OpenGGCM, LFM, and SWMF. And and then based on the the study, as you can see, usually the empirical models did not perform very well on these study. And this the empirical model are based on averaging geomagnetic measurements on the solar wind data. As also Weimer himself indicates in his 2013 paper, empirical model showed the mean steady state response to the specified IMF conditions, and it cannot resolve if there is a temporal changes and non-persistent changes. So and they had low score in Pulkkinen study. The other models that I myself are heavy user of that model is the MHD models, self-principal models. And there are physics-based numerical models that present magnetospheric response to solar wind. And they solve set of MHD equations. Usually all of them fits from the L1 points, and they run the model and they output most of the parameters. For example, dB/dt is one of their products. And this is the model, like for one of the model that has been used in forecasting at SWIPC is SWMF. And now we have other models to doing that one. doing the prediction too. But the caveat with this model is that they are computationally expensive for the high resolution runs. And if we run them like with the low resolution, that these DBDT might be missed and might not be well captured. So I think it's fair to say that current forecasting models, like MHD models, they struggle with prediction for near real-time forecasting. If you want to have them, the high resolutions one, and they need to have lots of infrastructure to do that. There are also has been a couple of machine learning models like that I'm aware of. I'm not sure, there might be some other things so I'm providing some example. There was a study by Amy Kesey and Victor Pinto at University of New Hampshire, and they used the SuperMag data, and they used different machine learning models, LSTM and the RNN-based models to predict the magnetic field perturbation in one station, Ottawa station. And there is an recently seen this Bailey et al. Study that they also use RNN to determine GAC, but is in Austria. So currently there is, to my knowledge, there is no model that uses machine learning, deep learning, and then can predict magnetic field perturbation. So then this is our model, the DAGGER model. So in this model, we developed a near grid-free global magnetic field perturbation forecasting model using deep learning to address the issue of the near real-time forecasting at both high spatial and temporal cadence. In general, this model is with a spherical harmonic basis, rendering the model near grid-free because we wanted to get the DBDT all over the globe. The model takes the solar wind parameters and the interplanetary magnetic field IMF measurements and the solar radio flux measurements as an input, and it generates forecasts of perturbation across the Earth with a lead time of 30 minutes. These forecasts made them be sampled all over the grid, nearly any resolution, owing to a global nature of spherical harmonics. And then when we predict these spherical harmonic coefficients, they can be translated to magnetic field perturbation, DBDT. So here is the data set we're using. At first, we came and then when we started running the model, we just gave them raw sample of solar wind, like BX by BZ and then VX by BZ. And our model was not performing very well. Thanks to Dr. Weimer, he actually used these features, we call good features to our model as an input to our model. So when we use these features instead of like raw magnetic field or velocity, our model was able to give better result. So these are the same, our input is the same as Weimer 2013 model. Also, we use SuperMag dataset, which is sampled all over the globe. But as you see, we only use the magnetic latch 40 degrees above, and that includes like around 175 magnetometers. The reason is that, as you can see, the SuperMag is mainly like distributed in the northern hemisphere, and they have a denser sampling rate than lower latitude, and we wanted to make sure that we get like kind of robust sample of the stations. So that's why we wanted to only focus on the northern hemisphere, but the model then can be expanded to the other part of the globe. So there are a few more details. The data that we used is from 2010 to 2009. And then the training set is used to train the models. We combine the model for when we do the machine learning. We have different buckets. So we use the training part, which is like for us is 80% to train the models. And then validation set is used to find the best model parameters that explains both the training and validation set. And then we have also we have that testing as well, so we could test the models. Um, since we have continuous time series of data, we almost cover 75% of solar cycle and then over the time. So we basically can go through we have data from solar maximum, solar minimum, and so we have all sort of data in there. And in order to obtain a long enough time series to avoid edge effects and mitigate bias from storm prevalence, we divide the whole time series into 100 buckets. So we wanted to make sure basically we don't have like these storms in our data set. We chose these storms from Dan Welling's study in 2018 that asked the community to focus on particular storms and particular validation mode. So in these buckets, we removed the 2000 and 2015 storms for the benchmarking, and the remaining buckets then splits are 80% for training, 10% validation, and 10% for the testing. So here is the spherical harmonic. So why did we use the spherical harmonic? Basically, as I said, we wanted to have a grid-free spatial coverage approach to get DBDT. And we wanted to have continuous and differentiable function form of over spherical symmetric manifold. The perturbation width should be larger, smooth, and avoid a localized peaks. So what happens is that basically we use deep learning to forecast coefficient of spherical harmonics, and then those can be translated to magnetic field perturbation. This is how we use the spherical harmonic in our study. And this is our model architecture. And the model has three principles. A time series summarizers, a coefficient generator, and a spherical harmonic connector. And constructed. The time series summarizes gated recurrent unit, GRU, into the solar wind time series and generate a series of hidden layers. So we get the solar wind data as an encoder, as GRU. And this is fed to fully FC layer, and which generates a vector of coefficient. These coefficients are contracted with the spherical harmonics bias to generate a spherical generate global forecast of perturbation. Our GRU cell is variant of the recurrent neural network. The GRU cell has internal memory in the form of hidden state, which is updated inputs are given into it. So this is our general forecast. So we get the solar wind, and then we give it to the hidden layers, and then we give it to spherical harmonic, and then from that we get DVDT. So we wanted to make sure that we benchmark our model. The three models that we use, and the first one is persistence model. In machine learning, it's easy to create persistent model. It's basic model that propagates the targets of the supermag at a time t to the time t plus some lag, where our lag is the time of forecasting, and we perform the model for each station. So this is just very basic. We want to see how much we are doing in our model does better. Does it do better than persistent model, or does it worse, or does it worth all these trying that we do? Another model that we are using is the empirical model. Dr. Weimer was kind enough to share the data of these storms with us. That's basically the spherical harmonic averaging that I showed you. So basically, Weimer and we use the same input, but we use deep learning and they use averaging. And the last model was Kisi and Pinto deep learning model that was using LSTM and I think RNN. I didn't put ANN. I didn't put it here for all the Ottawa station. So these are the three benchmarking models that we compare our model with. We also used, these are the validation metrics that we use. We use RMSE or root mean square error, and then the Y, which Y is the target, and then Y prime is our prediction. And we also use MAE, mean absolute error, the same. And these are all suggested in Welling study, and we are using those. And other things that we used skill scores. For that, we determine probability of detection. So basically, this is if the model hits it, and M is if the model misses a target, and probability of false detection. This is when the model gets false detection of the models. And I forgot what was the end. And then from that, we get the proportion correct, which is combination of these hit and miss. And then we get HSS. And then basically we are able to see how our model is doing in compared to previous models. These are from Pulkinen et al. 2013 study. So one of the parameters that is important to us, as I was saying, the GAC are related to magnetic field perturbation. And because the thing that is important is geoelectric field that leads to GAC. And then from that, you can see from farther is like how we get to dBdt. And the important part of contributed to GAC is actually H component of the magnetic field, that is combination of east-west component of the magnetic field and north-west component of the magnetic field. And then this is our dBdt. So this is our storm time performance, and the top one is the 2011 storm, and the bottom one is 2015 storm. This is our model DAGGER. This is the Weimer 2013 model. This is the persistent model. And note that this is not for one particular stations. Our metrics calculated across all times and all the stations. So we average everything. As you can see, the persistent model shows metrics only marginally better than the DAGGER forecast for the 2011 storms. In fact, the RMSE dB is lower for DAGGER. However, this is not the case for the 2015 storm. And also in general, our model has performed better than the Weimer 2013 model. And as you can see, none of the model is performing very good for the 2015 St. Patrick's storm. And so we will address that why this is going on. And in general, if we compare our output with the Weimer model, because our inputs were the same, it means that deep learning captures more nonlinear association between the solar wind and magnetic field perturbation, because, as I said, their input is the same. And we try to avoid just only showing our cherry-picked events. we wanted to see where we are doing worse, our model is doing bad, and where our model is doing good, and why our model is doing bad. So we decided to put best and worst forecasting stations. On the top, this is the IMF-BZ condition during the 2011 storm. This is the sim edge, which shows the storm's strength. And the panels are the different different panels shows different stations. For example, this is PTK, BRW, FSH, FSJ. And so these are different stations on the SuperMag. And on the left, we have our best performance, and on right, we have our worst performance. And in general, for the performance below the 250 nanotesla, we are doing better for the low threshold of dB. But one thing I want to take your attention, even though for the worst models, we do not see, like, we do not see the capture the peaks. We are able to capture those perturbation, but we are hitting like that threshold for that. And then for the, as you can see, these are for large MAE, like, MAE 100, and these are MAE of 18. So for these MAEs, DAGGER has hard time to getting the picks. But as I said, we are able to get some of these nice perturbation. And for our best performing, we are able to see all those perturbation as well. And I wanted to focus on the detailed performance of the worst performing stations. This is again for the August 15, 2011 storm. And these are, the blue is DAGGER, and then the black is the SuperMag. In general, the DAGGER forecasts the variation of the perturbation over time, even for the station with large MAE. It underpredicts the large perturbation value, which hence gives rise to a large MAE. Deep learning framework can estimate the solar wind measurements and generate salient association with the magnetic perturbation. The problem is the exact scale of perturbation is missed for the station with the large MAE. As you can see, like we get something, but we're not there yet. So these are the stations, is the same format. On the left, you see our best performing stations, and the right, you see our worst performing stations. And on the top is the IMF-BZ for this event. And this is the famous storm. You probably have seen it a lot, the St. Patrick's 2015. As you know, lots of data were missing for these storms. And for the 2015, and the perturbation of 300 nanotesla was a low MAE station. But like for the, as you can see, these scales, the scales has changed because you wanted to capture all the parameters. So note that like these are 300, these are like 1500 station. So large MAE stations have larger perturbations, and mismatch between forecast and measurements larger for low MAE station in 2015 storm compared to 2011 storm. And there is a larger spread in the joint histogram for low MAE stations in 2015 storm. So we need to do further analysis to see what's going on. Again, as you can see, we are able to get some of these perturbation even in our worst stations. Now let's look at our worst station in details. As I said, DAGGER is able to get the perturbations, but not the scaling right. Lowest and largest ME for storm was larger than those for the 2011. 2015 storm data has a lot of data gaps, and this is not seen in 2011 storm, so that might describe something. And larger MAE for 2015 storm may be due to the lack of the data. We did evaluation, and 24% of the data from the solar wind for this event were missing. And in general, I see, like, I use OpenGGC, and we struggle with 2015 storm as well. So this is the, okay, let me see. So this is the Sorry, I'm trying to get my panel. Sorry, where I can. I cannot play this one. Sorry. If I click one more time, yes, I'm able to play. So the video is showing the on the left target supermag, and then on the right our estimation from the DAGGER model. In it, as you can see, there is lots of dynamics, and our model is captured to get those dynamics, and then it shows how our prediction led to large MAE. And so this is one thing I wanted to bring to your attention. Another thing is that so we went and then we looked at the station with the max MAE, mean MAE, and then the mean of MAE. And for the stations, when we are on predicting, for example, here for the max MAE is the one we get max MAE. And for the ones that we are using, like, better prediction, for example, look at here, the super mag, and then there our model. The ones that we are doing better prediction, we are getting better MAE. So this is again for the 2015 storms. It shows the similar behaviors, and when we are on predicting, we are having large MAE. And again, here is like, for the max MAE, mean MAE, and the minimum MAE. And as you see, when we have better prediction, we have mean of MAE. So then we wanted to compare our model with other existing models, like, for example, for the model developed by Amy Kesey and then Victor Pinto. And you can see we have MSE, MAE for the Ottawa station, for DAGGER, Weimar, and persistent model. And then we determine different skilled scores for different threshold, 18, 42, 66, and 90. These are the threshold that has been introduced by Pulkinen et al. Study. And when we compare a result with Kesey's model for the 2011 storm, the DAGGER model performed than both models in POD and PC, but marginally worse in POFD and HSS. HSS, however, was higher or similar to LSTM model, but lower than ANN model. And for the 2011 storm, the DAGGER model outperformed both models in POD, but was marginally worse in PC, POFD, and HSS, consistent with average performance across all the stations for the 2015 storm. Again, suggests the dependence on the data imputation scheme. So going to my talk was short. I'm going to my summary. We developed a global model of predicting DBDT using deep learning on a spherical harmonic. We benchmark and model against the persistent model by Amy Kesey, and empirical model by Weimar. In general, our model performed a little bit better than the other models. And one important message from this talk is that the deep learning captures more nonlinear associated between the solar wind and geomagnetic perturbation, because this is because we, in the Weimar model, we both use the same input, but we were able to perform better in general. If you click on, if you scan this one, you're able to see our paper in a space weather. And some thoughts that I would like to bring out, because I'm personally both numerical user and then machine learning user, and then there are lots of problems in our like model forecasting model. For example, none of the models in the community can capture the high DBDT, 1.9 Tesla per second, and this is the important threshold. This is the threshold that triggers GIC. And this is what is missing in our community. And while like we find that while MAE or MSE are good detector of magnetic match of the forecasting, they cannot pick out the variations or capture with specific threshold. They cannot show for the specific threshold what is happening. Another problem in our community is that the skill scores that we are using is good, and it has been used. These are the only things that have been used, but these have its own baggage with it. The problem with this approach is that as you saw magnetic field perturbation, they are very localized. And for example, if model predicts perturbation slightly at different location, lower latitude, which is definitely possible, the model gets penalized for that and doesn't get a good skill score. And another thing that we have problem in our community is that the models do not provide uncertainties. Like for this, there are some models that are going to uncertainties, but most of the models do not have uncertainty estimation for the perturbation forecast. Because I think it's important because the uncertainty estimates both provide a degree of confidence and also inform us about the ill constrained regions for the forecast. So it's important we incorporate those uncertainties. And my last slide is about our future work of FDL. This year we have FDLX. This is the first time that we are going to integrate all the models that happened in the heliophysics. So one of the model is the DAGGER model, our model. Another is prediction of EUV irradiation. And then another model is the Karman, which is for atmospheric drag proxies. And we are trying to see if how we can combine these models together. Is there pipeline that we could that has been used for one model that we could use for another model? Can we get the data from the solar? Like now we have like the DAGGER model or the Karman model. They have 30 minutes forecasting time, and we are hoping with the model, with the sun model, we would be able to have like 2 or 3 days of like advances. So stay tuned. I'm a faculty this year and for the DAGGER model, and we're going to have lots of community outreach. We're going to have lots of live about our model development. So stay tuned about like our result. I think lots of interesting results will come out. And that's it. Thank you everyone for listening to my talk.
Thank you, Bashi. Now let's move on to the Q&A. Anyone has questions from the audience? Oh, looks like you have explained everything clear enough. Yeah, don't be shy, just unmute yourself. Okay, I remember last year there was last year? There was a GIC workshop in Boulder. I'm not sure if you attended that one.
I was not able to attend that one, yeah, but like I think another workshop is coming this year in Maryland, Baltimore, if I'm not wrong.
Baltimore, right? Yeah.
Yeah, Baltimore, yes. And then yeah, I think yeah, another thing is missing is like we're like the people from like electrical companies, and then us, like we are very apart, and then we do not have lots of like communication. Hopefully we can get to that. And we're trying with the DAGGER, we're trying to see if we could get in some stakeholders with to help us to go to the from DBDT to like at least geoelectric field, if not GIC. And so well, we're hoping to get something done on that regard.
I see, I see. So could you just remind me again, what time scale are you referring to when you say those are very transient DBDT?
Sometimes so in order to trigger GIC, I think there should be certain should have like certain time scales, but then for the in general they could be like in order of a minute and yeah, so yeah, they're very like fast, as you saw. The movie was like changing rapidly in 1 minute. There could be a couple of seconds, but for them to trigger GIC, I think they should they should pass like 10 minutes or something like that, like trigger GIC, or like people here are better than me on that. Like if they could correct me if I'm not stating it right.
Yeah, I know. In GEM, actually, there's a GIC related folks group. Shirley is sharing that. Probably we'll hear more talks over there. Yeah, I got another question. So certainly, this is a very challenging task by predicting the ground perturbation from like the origin, the solar wind. So maybe I missed it in your talk, but have you analyzed how like a small deviation in the solar upstream solar wind would impact the results on the ground? Like how sensitive is that?
We have not, but yeah, that's a really excellent point that we could use how like the small transient, like yeah, this is like our first like result out, and we have not tested the model. Yeah, definitely we have to do that. Another thing is missing, I think could be benefit our model, is that with our model, like for physics-based model, we have lots of false principle solutions that is there. But for our model, we do not have the history of magnetosphere. We have the solar wind, but it has been very hard to train in both super mag data and then solar wind. So we are hoping that the next step would be like we have training on super mag, so we could get a little bit of history of the magnetosphere before we run the model. So that might improve the model a little bit as well.
I see. Also related to the solar wind driver, so like in many MHD modeling, including both OpenGGCM and like Camera we're using, so we just rely on the technically is a single point measurements by ACE or Discover right at upstream, and we assume it's like a planar structure of a solar wind, but we know the solar wind in reality is certainly more complicated than that. So what's the potential of your model dealing with 3D structure of solar wind?
So I hope like this year, like I'm like trying to negotiate, like I'm trying to talk with the Sun people. Are they able to give us like because as you said, the L1 point is just like 1 point, and then if it's a hit or miss, and we know like the solar wind has like these big structures from like Brovsky's amazing papers, and so yeah, we're like, I was talking to them if there would be a way they could give us ensemble of PZ. I think in the future is coming, but I'm not sure how fast is that coming. The future is that we probably get ensemble of BZ, and then we run the model like with the different ensembles, and we get some ensembles. I think this would be the future of the forecasting model. It's not like you have 1 point and then you run the model once and then this is the prediction. No, we have to run model a couple of times. That's why I think for forecasting, I'm thinking that the future would be machine learning than like our numerical model, because they have ability to run faster for those ensemble modeling than numerical models. Yeah, so we're hoping to get like some structures, but I'm not sure. I hope with this FDLX, we get to certain point that we could do something.
Yeah, that'd be very exciting to see the future progress. And another question, since you know, I have been working on physics first principles models myself, like the coupled geospatial model. So I'm really, I'd like to hear your thoughts that how these machine learning or AI-based models can inform the improvement of first principles models in the future.
So to be honest, like, when we first started creating this model, we, instead of, like, informing the MHD models, what we did, we used the MHD models to, like, use the MHD models to inform the machine learning models. And also what we did, the result was not, like, because it's very hard to have continuous run of the, like, these MHD models, like, especially during the storms, like, after while the models go to the, like, some sort of, like, instabilities, so it was hard to get it. But, like, we have, like, I have some slides, I don't know where I can show you, but, like, we used OpenGGCM, and then we actually applied machine learning on the OpenGGCM, and then we wanted to see how our model is performing. So basically, we trained like, parameters in the OpenGGCM, and then we see how, like, the forecasting happens. The result was good. The result was showing, like, we are using good, like, we wanted to see how, for the spherical harmonics, which parameters are the best, and then how many modes should we take. So the result was good. Yeah, so it's possible, but I'm not sure exactly how can we do. I think Enrico Campriel's one of the gray models that he had, it was one of the approaches. But yeah, there are definitely some ways to combine the models.
I see. Yeah, certainly. I think, yeah, I need to learn more about how these two types of models can interact with each other, the physics-based and the machine learning-based. So yeah, let's just ask again. Anyone has a question for Bashi? Okay, looks like you're done. Excellent job. Okay, yeah, thanks again, Bashi. Really great to have you here. Hope to see you in person in the future.
Thank you so much. Thank you so much, everyone, for attending. Have a good
Yeah, thank
rest
you,
of your
everyone.
afternoon. Bye.
Okay, bye.